Forensic toxicology. The role of a toxicologist is to detect and identify drugs and poisons in somebody's blood and bodily fluids. Generally speaking, we're working with blood. More often than not, we're working with blood. They can also work with semen. They can work with vitreous humor extracted from an eye of a decedent. They can work with semen. They can work with other bodily fluids. But overwhelmingly, they're going to probably work with blood. Their workload is determined by the popularity of the drug. The more popular a drug is, the more tests they're going to end up having to run on it because more people who are being screened for drugs will show up presumably positive for these drugs. So legal drugs that may be screened for really, really frequently include alcohol, the most popular drug in the world and through all of history, marijuana, which isn't exactly legal, but it is decriminalized and frankly just super, super popular. So they're going to have to screen for that a lot. Medical drugs that can be used in a medical context include cocaine. Alcohol could be used in a medical context for somebody who's coming off of an alcohol addiction, paradoxically, for certain amphetamines. And to determine then, to compare whether or not any of these are legally prescribed or legally used for that person. Generally, if you're screening for cocaine, that's not going to be of a legal use because you're only supposed to use that surgically, topically. Amphetamines, though, can be used and can be prescribed for regular medical reasons. In this unit, we're going to be focusing on alcohol. We already talked about drugs quite a bit. Now we're going to be focusing on alcohol. Again, it's the most popular drug in the United States. It's the most popular drug in the world, and it's the most popular drug through all of human history. One of the first things that humanity came up with when we started civilization was beer. We've been doing it forever. Tons of animals love to seek out fermented fruits and stuff. This is a very important substance to the history of humanity. Because it's the most popular drug, it's the one that's most commonly screened for. The effective ingredient in beer, wine, spirits, whatever, is ETOH, which is alcohol. So it's a colorless fluid that has a very distinctive odor. You know this odor. You crack open a bottle of rubbing alcohol, or what am I thinking? Like vodka. You can smell that sort of astringent whiff very, very clearly. See diagram. Okay, so when you digest alcohol, you're going to consume it in the mouth. Some alcohol will be absorbed directly by the mucous membranes in your mouth. This is a water-soluble compound, and it can diffuse pretty freely anywhere where the blood vessels are very close to the skin. In your non-keratinized skin, inside of your mouth, on your tongue, wherever, alcohol can pretty freely diffuse straight into your bloodstream. It'll go down your esophagus and ultimately into, this is drawn backwards, but okay, the stomach. Some alcohol is absorbed across the stomach wall. Then you get into the small intestines from the stomach, which is a very, very, very long tube. It's like 12 feet or something like that in every person, but it's wound up into this like tight little wiggly pattern so that it doesn't take up quite as much space. It's packed in very efficiently. The role of the small intestine is to absorb stuff from your food, nutrients, fats, sugars, chemicals, whatever from your food. And then your large intestine sucks the water out of your food so that you can have formed feces when you excrete it. You're not just excreting loose stuff that's going to be corrosive to your skin and get everywhere and just not be great. The overwhelming majority of the alcohol that's absorbed is through your bloodstream, or is through your small intestine into your bloodstream. Some gets absorbed through your mouth, some gets absorbed through your stomach, most is absorbed through your small intestine. This is a little bit contrary to what most of us think of. We think of alcohol as being digested mostly in the stomach. That's not true. It does irritate the stomach lining really substantially, and I think that's probably where that perception comes from. Once it enters the bloodstream, and that's what this diagram has, it's going to enter predominantly the venous system. That's bringing blood back to the heart. And that's the type of blood vessel that's closest to the surface of your skin and any of your membranes. So it's going to be the thing that's going to take up blood most. So as it's bringing blood back to the heart from the gut, it's first going to have to pass through the liver. All of the blood from your gastrointestinal system gets shunted through your liver for processing, so that all of those nutrients and, like, your sugars, your proteins, your vitamins, your toxins, your whatever, can be processed by the liver into, sometimes it's going to turn unusable forms of something into something usable. Sometimes it'll pick up excess and pack it away. Like if you have lots of sugar in your bloodstream, it's going to pick up that extra sugar and store it away in this medium-term storage molecule called glycogen before that glycogen turns to fat. It can detoxify stuff that it finds that your bloodstream shouldn't have. It takes care of all this stuff. I mean, it filters all of your blood constantly. It's very, very, very thorough in its job, and it's very, very large in a person too. And then it takes that blood and puts it back into your heart. Now, when you're consuming your alcohol, some of that blood is going to be left over past the liver, and it's going to go up into the capillaries of your lungs. That's the next place after your heart that blood goes. The tissues of the lung are extremely thin. So alcohol can pretty freely vaporize from a liquid form in your bloodstream to a gas. This is important in alcohol detection, as we'll see later on. Because it's water soluble and because it travels through your bloodstream, it's mostly in your venous system, which is mostly going to get shunted over to your liver, but it does go everywhere into your bloodstream. It's going to enter your brain very, very quickly, within just a few minutes. It's easily taken up by most cells. And again, as we discussed in the drug lecture, because it's water soluble, it also gets excreted fairly easily. It also has a very low vapor pressure, which means that once it's exposed to the air, it has only a very thin membrane between itself as a liquid and the air. It vaporizes pretty quickly. It just sort of like evaporates away pretty easily. So you're going to absorb your ethyl oxide, your alcohol, and after that you're going to enter what's known as the post-absorptive phase. It's basically the digestive phase after you concentrate fully. How quickly you actually absorb that alcohol can vary tremendously. It is somewhat predictable, but it's not exclusively predictable. How big the person is, size of the person, matters. If you're 5'0" and 100 pounds, you're going to be affected by whatever alcohol you absorb. Your blood alcohol concentration is going to increase more quickly than somebody drinking the same number of drinks who is 6'5" and 300 pounds. The quantity and quality of the food that person already has in their digestive system, food is going to absorb whatever liquids that you consume to some extent. The food in your stomach and the food in your intestines is going to soak up some of that liquid. If it's alcohol, then it's going to absorb some of that alcohol. And if that alcohol is being absorbed up by food, it's going to diffuse into your bloodstream more slowly than if you didn't have anything at all in your stomach. Certain kinds of food will take up that a little bit more effectively, and some won't. Protein-rich foods, heavy foods are good sort of absorbers / blockers of alcohol from getting into your bloodstream. Pure sugary stuff like chips or pretzels or candy is much, much less effective. How long ago was your last meal? If you've eaten that last meal so long ago that it's through your digestive system mostly, it doesn't matter. The sooner you start drinking after you eat, the more effective your food can be at absorbing some of that alcohol and slowing the rate at which it affects you. how quickly you consume alcohol, how many drinks per hour, the type of alcohol. This is mostly referring to concentration. So like beer maxes out typically at like 12% alcohol, and that is a stiff, strong beer. More often than not, you see somewhere between 4 and 8% alcohol by volume. That means out of however much liquid, the volume of liquid in there, what percentage of it would actually be alcohol. So beer, 5-ish% alcohol. It can go up to as high as like 8, really unusually as high as 12. Wine tends to be more like 12%, so it's more concentrated with alcohol than beer. If you get something like a fortified wine, and that's, you can think of that as more often than not like your fancy after dinner wines. You think of like a fancy person swilling something after dinner, like sherry or port. That's stiffer than regular wine. A cordial or a liqueur, which is a sort of usually a sweeter dessert-like preparation of alcohol that is based on liquor but is not purely liquor, tends to be somewhere around 24. Something stronger like brandy is more concentrated still, and liquor tends to be very concentrated with alcohol. And as you'll notice, the percentages keep going up and the volumes keep getting lower. So this is a deceptively, the diagram makes it look like the increase of alcohol is less steep than it really is. One serving of liquor is only about 1.5 ounces. That's a standard shot glass. The proof is twice what the actual percentage is. So like 40% alcohol is 80 proof, 100 proof alcohol is 50% alcohol, for reasons that I frankly don't remember. But like a serving of beer is 12 ounces. So the type of alcohol matters mostly insofar as how concentrated the alcohol is in that drink. And finally, your liver quality. This is your real wild card that you have less of an easy time predicting or controlling. If your liver is already pretty damaged, it's not going to be very good at filtering out alcohol. So that alcohol can more or less pass your liver and stay in your bloodstream for longer and do more damage. You have an enzyme in your liver called alcohol dehydrogenase. That helps break down alcohol into safer forms. Alcohol is literally a toxin in your bloodstream. It's bad for your cells, and so your liver takes pains to make sure it gets degraded. The more damaged your liver is, the less of that you have, and the more of an impact any given drink will have on you, the longer it'll stay in your bloodstream. If you have hepatitis, some people have hepatitis and don't know it yet. That reduces your liver function. That's necessarily a disease of the liver, and you're going to be more affected by alcohol. If you're on certain prescriptions that are already using your liver to metabolize them, you're going to have basically less liver bandwidth to be able to break down your alcohol. That'll affect you more. If you just naturally maybe don't produce as much alcohol dehydrogenase as somebody else of the same size as you, you're going to get drunker faster. And that's not something you can control. And these are not always things that you can know. You don't know how damaged your liver is. If you've been obese your whole life and you've been eating fatty foods your whole life, that's a really heavy strain on your liver. People who are chronically obese are developing fatty liver disease and basically like a scarring liver that's not dissimilar from people who have not been alcoholics necessarily, but have been a pretty heavy drinker their whole life. That'll reduce how effective your liver is at taking care of the alcohol so that it doesn't affect you mentally as much. And then so it'll affect how quickly you can meaningfully absorb your alcohol. Breath testing is going to measure unmetabolized alcohol, the breathalyzer test. So you remember how I mentioned that the alcohol goes in your bloodstream, and then eventually some of it is going to make its way to your lungs. A lot of it's going to get neutralized in the liver, but some of it's going to pass through, some of it's going to go through other routes and end up in your lungs. In your lungs, you have these tiny little air pockets called alveoli. These alveoli, the lining of this wall is one single cell thick. One cell thick. And these are flat, skinny, skinny, skinny little cells. Around that, you're completely surrounded, and I'm just going to use blue, but even though that usually only indicates veins, but you have arteries and veins completely surrounding this alveolus. And the point is that the oxygen that you inhale can very easily pass that one layer of cells and go into your bloodstream, so your blood can get oxygen. And then when your cells have too much carbon dioxide, carbon dioxide is a natural byproduct of metabolism. It'll dump that CO2 into your bloodstream, and that can easily percolate out so that you can exhale it. There's very, 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 very little barrier between your blood and the air in your lungs by design. Now, alcohol would be absorbed in your body and travel through your blood. When it gets to your lungs, remember alcohol has a really low vapor pressure. It vaporizes really, really easily when it's exposed to air. This is really, really close to being air. So when blood gets close to the surface and gets into your alveoli, it can vaporize out and can be exhaled. Now, this is a measurable thing, and that's what the breathalyzer technology exploits. You're not going to exhale all of your alcohol, right? You're going to sweat some of it out. You're going to urinate a lot of it out, but you'll exhale some of it out, some small amount. And it turns out pretty reliably that 1/2100th is what's going to end up being exhaled. What this breathalyzer will do is it'll take the exhaled breath and it'll measure it on the inside by infrared detection. Some of it's a chemical reaction. Infrared's more popular. It'll take the concentration of alcohol it finds in your breath, multiply it by 2100, and get this figure. 0.08 in the United States is the border between you being allowed to drive or not. And so if you're administering a breathalyzer, you're trying to determine level of intoxication for some purpose, and typically it's driving. So it'll give you that readout right there. It's super easy to use. You can buy one on the internet and use it at home for fun if you really wanted to, you know? You don't need any training. You're not even going to need to look at the manual. You know the 0.08 number is the can you or can you not drive. You just breathe into it. That's kind of it. Super inexpensive to purchase, very easy to use. The results are totally intuitive. It just gives you a number, and you know the boundary number that you need to be less than for it to be cool. So it's super intuitive to understand. And this ratio is really well documented in medical literature. So there is some variation, you know, person to person. Everyone's a little bit different, but not enough to matter. So in almost every aspect. So this multiplication, frankly, of the concentration is pretty reliable. The cons are mostly in user error or user variation. You need sufficient breath. You need to be blowing through there anywhere from 1 to 1.5 liters of air. That's a volume of air, like a physical amount of air, space, for more than 6 seconds at a total rate of more than 3 liters a minute. So you need to be pushing a lot of air out of your lungs fast into this machine for it to properly read it. If you are drunk and you're trying to exhale that fast, you might very well just pass out. That's if you have emphysema, if you have asthma, if you have COPD, if you're fighting off a nasty cough or cold, this is going to be really hard to do without getting dizzy, without falling over. And it might just be hard to do, period. If you're small, if you're 5 foot tall and 100 pounds, that might be a really, really hard push for you to accomplish. If you're 6'5" and 300 pounds, you know, maybe exhaling that much air in that amount of time is less difficult for you. For most of us, this is a real solid breath. Person could pass out. Smaller people might not be able to give enough breath to properly do it. And if you have lung issues that affect your exhalation or how effectively you can exhale, then that'll really throw it off too. It can be easily thrown off if you don't have a proper seal around this mouthpiece. You'll end up exhaling some of that into the environment and not into the machine, which can throw it off. If it's been a little while since you've had your last drink, even if your concentration's kind of high, not as much might be coming out through your breath anymore. There's a lot of, frankly, tricks that you could do to get around the breathalyzer a little bit. If you're borderline, it can end up showing you as being safe, even if it's not. Every time that you exhale, you're going to give a slightly different concentration of alcohol. This 1 to 2100 ratio isn't static with every breath. It just averages out to that ratio. So one exhalation might have a blood to breath alcohol ratio of like 1 to 1500, and the next one might be 1 to 3000, and the next one might be 1 to 2500, and the next one might be 1 to 1500, and it averages out to 1 to 2100. So that one breath that you gave might not be representative of your breath as a whole. So if you're doing the breathalyzer, not only should you be really huffing out some air quickly and a lot of it, but you should do it a bunch of times. That's not super easy to actually accomplish. Typically on the road, they're only going to give this to you once. They should give it to you more than once, but more often than not, they're going to give you the once, and then they're going to haul you in to get a blood test if it comes up positive. So, I mean, on one hand, it's super cheap, it's super easy, it's a decent enough of a rule out mechanism for determining if somebody's legal, say, to drive, for example. But is it super reliable? Is it something that if that's the only information that you had, could you feel safe that you could convict somebody about? No, not really. You want something a little more solid. Another way to determine somebody's sobriety or how inebriated they are, how mentally affected they are from alcohol, is to do a field sobriety test. This doesn't actually detect the alcohol concentration in your bloodstream at all. It's there to detect impairment level. This historically has been the most popular way to detect alcohol concentration, or to detect how inebriated somebody is, how affected by the alcohol somebody is. And since it doesn't require any kind of technology or equipment, it can be pretty easily employed basically anywhere as a way to determine whether or not more screening is necessary. There are some common routines that people will do. Horizontal eye nystagmus. This is like a shaking of the eye. We all have a little bit of that. If you look at somebody's eye when they're focusing on something, you'll notice it's never exactly still. It moves just a little bit all the time. If you have somebody follow the tip of your pen with their eyes and eyes alone, if you follow smoothly, that suggests not that the person is not inebriated. If the person's eyes sort of flutter around while they're following the pen, then that suggests that they're inebriated. Alcohol is a depressant. Alcohol is a depressant. And if you recall, depressants slow your reaction time. They, among other things, I'll just leave it there. Oh, well, it's a depressant. It slows your reaction time and it impairs your muscle ability. It's a little bit of a relaxant. You have eye muscles around your eye that's helping you keep up. So one of the things that alcohol will do is sort of make those eye muscles a little less controllable, easily controllable. So your eyes will flit around a little bit. Walk and turn. This is sort of exploiting the fact that you get more easily dizzy if you have alcohol in your system. You're a little bit dehydrated, and it throws off the mechanisms of your inner ear that do balance stuff. So you walk in a straight line, usually heel to toe, so you're sort of on as narrow a path as you can, and then turn around quickly on that same line without falling over. The more easy that is to do, presumably the less inebriated you are. One leg stand exploits the same thing, but with no movement. You're asked to stand on your leg. Another one, touching your finger to your nose, because your vision is thrown off with a lot of alcohol. You might not be able to coordinate yourself properly to get your finger to your nose. These aren't reliable basically at all. They can be something to do while you're waiting for other indicators of alcohol inebriation. It could be considered a rule out kind of a technique, but it doesn't actually tell you much about person's blood concentration. The horizontal eye nystagmus can happen for a huge variety of reasons, one of which being alcohol intoxication. So just because your eyes are doing that doesn't mean necessarily anything to do with alcohol. Walk and turn. I don't know about you, but I have crappy balance. I would fail that. And when I demonstrate this in a real life class setting, I routinely fail this with no inebriation whatsoever. Depending on the person's shoes, it might be harder. If the terrain is uneven, I mean, you're doing this on the side of the road, there's like gravel and stuff. That's not super easy to do. A one leg stand, also balance. My balance isn't great under the best of circumstances. If I'm getting pulled over and I'm under enough suspicion that they pulled me out of the car to have me do one of these, I'm also super nervous and kind of shaky. I'm not able to accomplish any of these anyway. Another test that they might have you do is to do like math backwards quickly, or say like subtractive math quickly in some weird amount, like start from 100 and count backwards by subtracting 7 every time. How well can you do that? Or say the alphabet backwards. These are memorizable things, frankly. And so if you decided that you wanted to pass this test and still drive drunk, you could just memorize it. And if you had memorized it thoroughly, you could just recite it. There's a lot of ways to get around all of these things. And it's not, the field sobriety tests are universally pretty unreliable. It can help, failure to perform a sobriety test can help support your case for them being actually impaired, despite whatever the blood alcohol concentration might come back as in a lab, but it does not stand by itself. Lab testing will detect alcohol concentration directly. We've talked a little bit about gas chromatography, where you pass a gas basically past a liquid, and then if the chemical of interest vaporizes out into the gas, you can detect that at the end with a computer and quantify it. Alcohol, as we have mentioned, vaporizes really easily, so it's super conducive to this process and can help determine the concentration of alcohol in somebody's blood very quickly. Of course, you will need to get a blood draw to do that. It can also detect byproducts of alcohol in addition to the alcohol itself. So if somebody has finished drinking a couple hours ago but is still drunk, they might pass a breathalyzer. They may or may not pass the field sobriety test. A lot of their alcohol might be broken down by now, but it's still, their brain is still affected by the having consumed alcohol. And so effectively, behaviorally, they're drunk. These gas chromatography techniques can detect not just for alcohol, but it can also be directed to detect the byproducts of alcohol. This is also important if you pull somebody over, let's say, and they're clearly drunk, right? You can smell it coming off on their breath. They're failing the field sobriety test. They're generally just acting impaired. You take them to the hospital to get their blood drawn, or you take them to the station or wherever they're going to get their blood drawn. Sometimes you're going to have to wait a long time. And by the time you actually get that blood draw, the person might have sobered up enough to get below that 0.08. By detecting not just the alcohol directly, but by the byproducts of the alcohol, you can determine how long it's been since somebody has been drinking and what their blood alcohol level was at its maximum before. This is very, very accurate, very, very reliable procedure, but again, it does require a lab. It requires a blood draw. Collection and preservation of blood. So you're doing a blood draw, you have to be able to collect it in an aseptic fashion, and you need to be able to store it in such a way that the blood doesn't dry out, it doesn't get contaminated, and the alcohol in that blood can remain present and stable for long enough to do lab testing on. First of all, first and foremost, they must be drawn by a professional, somebody trained in phlebotomy in an aseptic manner. Aseptic is any time you do aseptic technique is where you perform a medical process, a medical technique in such a way that you introduce no infection. It's sterile, effectively. You're going to employ universal precautions. Remember, you're dealing with biological materials, so you assume that all the blood you're collecting has infectious agents in it and that you are susceptible to, and you act accordingly. You wear 2 pairs of gloves, you wear physical protective gear, you have eye protection on at all times. You're going to make sure both of your gloves are on, again, non-latex. You'll apply a tourniquet to the person's arm up further, like closer to the root of their limb. So you're usually going to take blood out from the space in front of your elbow. I'm sure you guys have had blood drawn at the doctor's office or something before. That's where you're going to take it. Far more often than not. The only reason you're not going to take it there is if you can't find a vein, because the person's really obese or super dehydrated or sometimes super old, or if there's a lot of scarring there, if they've had a lot of medical procedures in the past, if they're an IV drug user, you might not be able to find a usable vein there. But I mean, ordinarily, for the overwhelming majority of us, that's where you're going to get it. So you'll apply the tourniquet further up their arm than that, and that's going to stop blood from their veins from getting back out of their arm and into the back into their heart. So you're going to create like kind of a pooling of blood in the arm for just a little bit. You're going to sanitize with an alcohol swab. So you're going to rub that patch of skin pretty vigorously. That'll help get rid of any kind of skin cells that are there. It'll rub off, frankly, some of the bacteria, and it'll kill basically all bacteria and viruses on that patch. Importantly, you need to let that alcohol dry before you apply the needle to their skin. Otherwise, some of that alcohol is going to go up into the needle and throw off your results. So let it dry. You'll draw with a needle directly into an appropriate container. And you've seen this at the doctor's office probably before. They have the needle, they have with the little butterfly clip at the end of it to help keep it in place. And to keep it out of your body any more than it has to be. And then there's a tube, and at the end of the tube, there's another little needle. And that punctures directly into the collection tube. So the blood drains through that tube and into this, it's also called a tube. It looks like a little vial, right? So the blood will go directly into there, meaning it can't get contaminated by any kind of fomites, any kind of anything in the outside world. And the alcohol from your bloodstream does not get a chance to evaporate into the air, okay? It's drawn directly into this container, which is sealed and self-sealing, that already contains a preservative and a coagulant. Usually, this is called EDTA. This chemical preserves the blood, keeps it from degrading, and it also helps keep it from clotting. If the blood coagulates too much, if it clots, you can't do tests on it. It's not a liquid anymore. And all these tests that you're going to do on blood are designed for it to be in a liquid state. These tubes come pre-prepared from medical equipment manufacturers. They are already sterile. They are already totally sealed. The type of tube that you're going to draw it into are one of these model top tubes. It's either gray with red or yellow with red, depending on what other testing you're going to need to do on your blood sample. These are standardized color codings in the medical lab tech world. So if you are doing this test in Massachusetts or California or Hawaii or Texas, you're going to draw into the same type of tubes no matter where you are. Okay? After you draw blood, the blood alcohol concentration cannot increase. So once you collect the blood from somebody's veins, there is no mechanism by which in this process the alcohol level could go up, unless of course you don't let that alcohol dry on their arm first. Alcohol dries extremely quickly when you're applying it in such a thin layer like that, so it's really not meaningfully a hazard, but it could be. The alcohol concentration, however, will decrease with improper handling. If you expose the blood to air after it's been drawn, some of that alcohol can vaporize out. So vaporization, I should add here, vaporization. If this isn't done in a sterile manner and there's bacteria introduced to the tube, the bacteria can degrade some of the alcohol. It can consume it. Alcohol is treated like a sugar by some bacteria and can eat it. Um, so if it's not done under proper aseptic technique, you could reduce the concentration in that blood between when you collect it and when you process it and evaluate it. If you don't refrigerate the blood, it'll decay faster than if you do. It does have a preservative in it, but that preservative isn't bomb-proof. You'd also need to refrigerate the blood to keep it fresh. If you don't use an industry standard tube, it's not going to be sterile necessarily. It's not going to have the proper preservatives and coagulants, and that can interfere with the alcohol concentration, or at least your ability to detect proper blood alcohol concentration from that blood. For deceased people, they don't have moving blood anymore, right? So it's a little harder to do this. You're going to draw a sample from multiple sites. Since your blood stopped moving, let's pretend this person was drunk, they fell, they hit their head, and then they died, right? The blood that's left in their body has stopped moving at some point. Alcohol was not completely absorbed necessarily and evenly distributed into their bloodstream. If you take a sample of blood from their head and a sample of blood from around their gut somewhere, you might have really dramatically different alcohol concentration levels. So you're going to take it at a variety of different places in their bloodstream as best as you can, and that can help give you an idea of what their maximum possible blood alcohol concentration would have been at the time of their death. You can also draw vitreous humor or urine from the deceased person. Remember, vitreous humor is that gooey kind of substance that's inside of your eyeball that keeps it nice and round and big. That can be drawn with a needle in exclusively dead people and evaluated for whether or not there is alcohol in it. Urine, same thing. You're going to excrete byproducts of alcohol in your urine and some alcohol directly. So you can detect some of it that way. You can only reliably do that, though, if these sites have not been really colonized with bacteria. Remember, after a person dies, their bacteria kind of has free reign to start to grow and take over. If the person's bacteria has invaded their urinary system, traveled sufficiently far up their urethra to affect their kidneys or their bladder, you may not be able to rely on urine evidence. If the person's eye has begun to break down, and that's one of the first things to really start to appreciably rot in a body, then the vitreous humor may be rendered unusable. BAC laws. The drinking age used to be 18 across the entire country for a very, very long time, but it was increased to 21 in 1984. An organization called Mothers Against Drunk Driving, you've seen MADD, I'm sure, on highway signs and stuff, had lobbied for this really extensively so that to reduce drunk driving deaths in the United States. The original purpose of these organizations, and it wasn't originally called Mothers Against Drunk Driving, it was a full temperance movement where they wanted to abolish alcohol entirely, but they found traction with this particular effort, and a segment of them became mad. They lobbied the federal government, and the federal government didn't exactly demand that all states change their drinking age to 21, but what it did is it tied that change to federal highway dollars. So the federal government is supposed to supply money to each state to maintain the interstate highway system within their state's boundaries, so that, in Massachusetts, they're not paying for the maintenance of I-90 out of their state budget. They have allocated federal money to pay for the maintenance of I-90. This interstate transit is not paid by the individual state. It's paid by interstate money. But what the government did then is they told the states, you're going to keep getting your money if you change your drinking age to 21. And if you don't, you're not going to get federal money. And different states moved at different times. I think Maryland, either Maryland or Wisconsin were the last ones to change. They stayed 18 for a really long time, and were paying for their own interstate highway maintenance in the meantime. I'm not sure why Maryland kept it for so long. I think it was just economic reasons. And I can never remember if it's Wisconsin or Minnesota. I think it's Wisconsin. Their argument was basically that they didn't want to turn away beer from, like 18-year-olds in the military. They didn't think it was right that you could fight a war, but you couldn't have a beer. So they didn't change it for a really long time either. Between 1939 and 1964, there was a BAC limit to what would count as drunk driving. There's always been some sort of drunk driving laws as long as we've had vehicles. And until 1964, it was 0.15, which is quite drunk. Now, they didn't have as good techniques for, like, aseptic technique for drawing. They didn't have as sophisticated techniques for detecting blood alcohol levels. So this is partly driven because of a reduced sensitivity of the lab testing, but it was also quite high. In 1965, it was brought down to 0.10, and in 2000, across the board in the United States, the drunk driving age was reduced to 0.08. For commercial drivers, it's different. The 0.08 is just for regular drivers, 0.04 for like truckers and stuff and taxi drivers. For commercial drivers, their blood alcohol level is very, very low. It's basically so low that you can't finish a drink. For most people, you can't really finish a drink and be legal to drive commercially. 0.08 for most people is around the pace of one drink per hour, without any kind of overlapping. So you can have a beer an hour and still legally drive for most people. For very, very small people, that's not the case. For bigger people, you could stand a little bit more, but you don't really know the state of your liver at any given time. That's your wild card. So most people should shoot for less than one drink per hour to assume that they're legal to drive. In the United States, this is actually quite high. In many, many countries, most of Western Europe and Canada and Japan and Australia, you have a really, really low legal blood alcohol concentration. In Sweden, it's effectively zero. So you can see in Russia, there is no tolerance for, in Poland, there's no tolerance for any amount of alcohol in their system. In Finland, and I think that's Lithuania, is that Latvia? In Germany and France, they have a 0.05 limit. UK is 0.08, but they're kind of considered lushes across Western Europe, and a little reckless with their drinking, so they have a little bit of a higher BAC accommodation. In the United States and in all of these countries, there's something called implied consent that is given when you get behind the wheel. So we've talked already about how you have to draw blood to get a good, accurate determination for how much alcohol is in somebody's blood. You also have to do you also can do a breathalyzer to detect it in their breath. These are medical screenings. You're screening somebody's physiological state of being, right? And so in medicine, you have to consent to procedures done to you by law. The law is, however, written in such a way that if you get behind the wheel, you are automatically considered to have consented to testing for inebriating substances, including, and most commonly, alcohol. So by getting behind the wheel, you effectively do not have any recourse to refuse breathalyzer and especially a blood test if it were to come up. Actual refusal to consent to these things is very, very damning in court. And while of course they're not allowed to like hold you down and take your blood, if you flat out refuse it, you're not going to get off on that charge. The toxicologist is going to take that blood that was withdrawn and analyze it for this given toxin, right? This alcohol. They can also analyze these fluids in this blood for a variety of other things. They can evaluate it for other illegal drugs. They can evaluate it for heavy metals. Toxicologists can also do like lead screenings to see how much lead is in somebody's blood. And they can detect poisons as well. Ideally, the toxicologist will have some sort of context to work with. You don't want to just get a sample of blood and not know what on earth it is you're supposed to be looking for. You're going to get a sample of blood along with a little bit of a story, along with a little bit of the case. This person was pulled over under suspicion for drunk driving, but they seemed a little extra agitated, so maybe you should screen them for cocaine too. Or this child grew up in substandard housing, very old, poorly maintained housing that still had a lot of lead paint in it from back when lead paint was legal. You should screen them for lead. This person has blue lips and blue fingernails, and we suspect cyanide poisoning. You should look for that. They're going to get some sort of a context to examine the blood. You only have so much blood that you can evaluate. You have a vial or two's worth of blood. So you want to make sure that whatever blood you're extracting for testing purposes is going to be used as efficiently as possible. Major challenges of the toxicologist include if the blood or tissue wasn't harvested at the time of optimal blood concentration. Some things are harder to detect after the fact than others. That alcohol byproduct situation, you can do that test. It's not as reliable as if you got it when the alcohol was still quote unquote fresh in your blood, but it's pretty good. You ideally want to get it sooner than that though. Oftentimes you don't have a super specific instruction. Like you're going to get blood and you're going to hear that they were pulled over for suspicion of alcohol, but they're also going to be directed to just look for whatever. This person was pulled over because we suspect that they're drunk. They can put in a vague statement like, we also suspect they might have drugs in their system. Please look for those. And every given drug that you're going to look for is going to have a slightly different test. You might end up using a lot of that blood, or maybe not even have enough blood to do all the tests that you feel that you would have to do to look for the things you're being asked to look for. More and more often, they're being challenged to look for drugs that they have never seen before, or that are really, really new to the market. So like when bath salts came out a bunch of years ago, there's not like a predetermined test that's already prepared that a toxicologist can do to look at somebody's bloodstream for bath salts. They have to reverse engineer it. They have to figure out what the molecular makeup of that drug is, and then look for those components in the bloodstream, and then also try to predict what the metabolic breakdown products of that are, and look for those, and then hope that they're right. Drugs will also change. So the common molecular makeup of methamphetamine 15 years ago and what it's commonly made up of now isn't necessarily the same, right? Pseudoephedrine in like cold medicines and stuff is harder to get in quantities that you could get it at 15 years ago. 15 years ago, you could just walk into the drugstore, get all of the, like, whatever, NyQuil, I guess, off the shelf, and buy 50 packages of NyQuil. The cashier would look at you weird, but you could do it. Now you can't. So the formula's tweaked a little bit, and that can affect the type of test that you would have to run to see if that's in their bloodstream. And also urine samples might not be super helpful. Sometimes all you have is a urine sample to go by, depending on the drug. You might have bacteria that can metabolize certain byproducts in there. It might not be of the quantity that you would need. If the urine had to sit for any amount of time, you might have had vaporization of, say, alcohol. It's not necessarily always super helpful to have urine. On a positive note, for those drugs that we are well familiar with, that have been with us for a number of years, we do have good, published, reliable data for these drugs. Remember, toxicologists are not just looking at suspected criminals' blood. right? The toxicologist looking at blood is going to be looking at these guys' blood and sick people, right? They're in a hospital or a doctor's office or something. They're going to be looking for alcohol in somebody's blood who is on certain medications. They're going to be looking for it for people who are about to undergo certain procedures. We're going to look for, and they're going to be looking for all of these drugs for medical context too. If you have cocaine in your system, you can't get certain anesthetics. The anesthesiologist needs to know that so they can change what anesthesia they give you for emergency surgery. Because these things are looked for in a solid scientific medical context, there's really good, reliable data for the detection of well-established drugs. So that is the good thing. Techniques of the toxicologist includes pH manipulation. So basically, certain drugs are going to be in your bloodstream if you change the acidity level, if you make it more acidic or more basic. You can use that tweaking of the blood or the whatever bodily fluid it is that you have to encourage selective extraction of certain drugs. Different drugs are more easily extractable in acidic conditions or basic conditions, and you can manipulate the pH of your sample to encourage extraction of that drug in particular. This is super easy to do. You have to do it in really small batches. This doesn't work effectively if you have several vials of blood all at once, but to do it on a milliliter here or there, you can effectively do this process. Chelation refers to the process of heavy metal extraction. You're not really going to be doing this so much with drugs, but a toxicologist would be tasked with doing this for looking for heavy metals in somebody's blood, most commonly lead. Screening techniques include TLC, which is thin layer chromatography. It involves extracting a compound by spreading it in a solution across a plate and then detecting that whether or not that came through the solution. We talked about that with drugs a little bit. Gas chromatography and mass spectrometry, we talked a little bit about that with drugs too. This is the method of choice. It's extremely precise. It's extremely reliable. And not only can it detect most things directly, it can also really accurately quantify metabolites of these things as well. For some really unique compounds, you can do immunoassay where you design antibodies that can bind to certain chemicals that you're looking for in a bloodstream and try to precipitate out those antibody chemical complexes. For heavy metals, you can do some other stuff that involves reactivity or that involves manipulation of X-rays. Metals will reflect X-rays and absorb at different rates, and so you could use X-ray diffraction. It's just a X-ray photography kind of radiology technique to detect patterns of things. Emission spectroscopy, I'm not going to go into that. It is a heavy metal detecting technique though. And spectrophotometry, which we've already talked about. Carbon monoxide can be easily detected by gas chromatography. Carbon monoxide is an important compound to look for in somebody's bloodstream because it is lethal. Carbon monoxide poisoning happens when, okay, so you know that you have oxygen in your blood and you need to inhale oxygen into your blood and then use that oxygen to feed your cells. Your cells need oxygen to live. The receptor site on hemoglobin, the protein in your blood, in your red blood cells, is super, super, super well fitted to an oxygen molecule. One of the only things that fits better in that space than oxygen is carbon monoxide. It fits in there snugly and tightly and doesn't dissolve out as quickly as oxygen. So carbon monoxide will get absorbed into your bloodstream and it'll effectively prevent the breaths that you take, the oxygen you inhale, from getting to your cells, and you can sort of suffocate while still breathing. Gas chromatography can detect carbon monoxide well. These types of screenings are also really popular for regular commercial use, as I've mentioned. These are all techniques that you're going to use for other reasons in a normal hospital setting. Finally, it should be stressed that ultimately with many of these tests, there's going to be subjective analysis of objective results. What's nice with all these techniques is you're going to get objective results. You're going to get numbers, right? That are direct reflections using well-established techniques to tell you what a concentration of something is. Taking that number and using it to determine the amount of impairment somebody was experiencing or the behavioral changes somebody might have had is really, really subjective. Extrapolating known biological toxicological data, putting it together with other factors, asserting impairment for legal reasons. The known concentration of drugs can only suggest the degree of impairment that somebody was experiencing. Some people do have tolerance to some things where you have a concentration of X in your bloodstream, but you've been consuming that and keeping your blood up at that concentration so much for so long that no longer inebriates you. So just because you have that number doesn't necessarily mean that you are inebriated the same as somebody else with that same number. That analysis is subjective. You can solicit a police report that can help describe the person's behavior. That can help suggest to a jury, for example, how inebriated a person really was. But that's a super, super subjective record. The police officer is not just writing down with no adjectives what they see. They're going to pick certain descriptive words, and they're going to pick them for a reason, which isn't going to be completely absent of their own biases. Urine tests, like I had mentioned before, they can show sometimes the presence of the drug, but depending on how contaminated it is, how old it is, whatever, you may or may not really be able to do that. And just because you're excreting a drug doesn't necessarily mean you're still under the influence of the drug. So you relying on a urine test to show presence of a drug doesn't necessarily link that drug consumption with the time that's important that we're considering, right? Just because you find alcohol in somebody's urine doesn't automatically mean that the person was still under the influence while they were behind the wheel. The timing can be really hard to determine. Finally, you could get a report from a DRE, a drug recognition expert, that can that presumably has sufficient training and expertise that they can reliably assert these types of connections. There's not really a whole lot of scientific basis behind a lot of this training. It's anecdotal in nature. It's sort of broadly trend-based in nature. Some people are very, very good at doing this, but just because you have this expert looking at the data, it doesn't or attesting to the data, it's still a really, really subjective analysis ultimately.